Homework 3, problem 1. Find the electric field everywhere for these two situations, a solid sphere with uniform charge density rho naught and a cylindrical shell with uniform area charge density sigma naught, and then show that the difference of the electric field at the surface is given by the following formula known as the electromagnetic boundary condition. And so to start out, we're just going to use Gauss's law to actually find the electric field. We've done this before for this exact situation, and so we know how to do this. We're going to draw our Gaussian surface as a sphere. The normal vector of the Gaussian surface is of course in the radial direction, and we're going to assume that the electric field is only a component in the radial direction, only depends upon r, does not depend upon r vector at all. Okay, so taking this, the integral form of Gauss's law, and this is true for both of these situations, is that the flux of the electric field through the surface, so integral d2x n hat dot electric field is equal to the integral of the charge density over that surface, okay, over this volume, delta V. So for our spherical symmetry case here, we've already made the assumption that E is in the radial direction, our n hat is also in the radial direction, and so n hat dot E is just going to be E sub r. And so since this is uniform over the surface, since r doesn't change over the surface of the sphere, on the left-hand side of the integral form of Gauss's law, this is going to give us 4 pi, we have to choose a radius, we're going to make that little r squared, times n hat dot E is just the r component of E as a function of r. And then we have to evaluate this side. This side is going to have two different things. If our sphere is, if our little r is less than big R, what we're going to have is just the volume of the sphere, so 4/3 pi little r cubed times rho naught, and this is for r less than big R, or we're going to have the volume of the sphere itself, which has capital R, so r cubed rho naught, and this is for r greater than R. And so taking this, we get that the electric field is going to be so rho naught over 3 epsilon naught. There's an epsilon naught here, an epsilon naught here, I always forget that. And then we are going to have this case, right? This goes as r for r less than r naught, r vector, sorry. And this goes as capital R cubed over r vector squared r hat for r greater. So that's the electric field for that case. Taking this and going forward, when we ask to find we're asked to prove the electromagnetic boundary conditions using this, which we want to find that sigma, which is the charge density on the surface, should be equal to n hat dot epsilon naught E above minus E epsilon naught E below. And so this is what we're asked to find, and so what we have to do is we look at E above. So E above is for r greater than r naught, as we take the limit as little r goes to capital R. Luckily n hat and n hat is little r, so that is still going to be the same. So epsilon naught E above, or n hat dot epsilon naught E above, is going to be equal to the limit as little r goes to big R from above of So this is going to be rho naught over 3 epsilon naught r cubed over little r squared, which is going to be rho naught capital R over 3 epsilon naught. Similarly, n hat dot epsilon naught e below is the limit as r goes to r from the bottom side, rho naught over 3 epsilon naught of little r, which is rho naught capital R over 3 epsilon naught. And so the subtraction of this from this is of course 0, and so it says that the surface charge at the surface of this is 0, which is exactly what we want to find, because there is no surface charge. This is a volume charge density, not surface charge density. So that is kind of interesting. That says that a volume charge density and a surface charge density are somewhat different. So that's kind of an interesting conclusion there. We're going to do the same exact thing for the cylindrical case, and for the cylinder, our Gaussian surface is, of course, a cylinder around the axis of symmetry, and we're going to make the height of the cylinder capital L and the size of the cylinder S. Then for the left-hand side of this, the other thing is we have, of course, that our n hat is going to be equal to the s hat direction, and we're going to say, for reasons of symmetry, that the electric field in this case is only going to be in the s direction, and our other n hats are here, and these n hats are in the plus or minus z hat direction. So whenever we take this n hat dot e, the n hat dot epsilon naught e, the z hat dot s hat gives 0, and so we get no contribution from the top and bottom, so we only get contribution from the side. Now, since this n hat dot epsilon naught e is going to be constant at a given s, so over the whole surface it's constant, this integral is only going to give the surface area on the side of the cylinder, so that's the circumference of the cylinder, 2 pi s, times the height of the cylinder, L, and then the n hat dot epsilon naught e will give epsilon naught es as a function of s. On the right hand side, we're going to get 0 charge inside for s less than a, and for if s is greater than a, we're going to get whatever charge is kept inside. So that will be the surface area of the cylinder inside that. So that's going to be 2 pi a times L for s greater than a. Okay. Solving for the electric field, then, we get that the electric field is a function of r for the cylinder. So let's separate these two. The electric field for the function of r cylinder is going to be, oops, I'm missing a sigma naught here. 0 for s less than a, and it's going to be sigma naught a over epsilon naught s hat over s. Is that right? That's right. For s greater than a. Okay, and so that's the electric field in the cylinder's case. And so now we want to come down here and do the same thing we did before. We want to check the electromagnetic boundary conditions for the cylinder's case. So let's separate those. And then we're going to use the same equation again, that sigma should be equal to n hat dot epsilon naught E above minus epsilon naught E below. And we're going to use this form of E, and so n hat dot epsilon naught E above, we're going to say above is outside the cylinder. This should be equal to the limit as S goes to A from the positive direction of sigma naught A over epsilon naught S. Oh, the epsilon naught goes away, that cancels with that one. Which is of course going to be equal to sigma naught. And n hat dot epsilon naught E below is going to be the limit as S goes to A from below of 0, which of course is going to be of 0. So this minus this is just sigma naught, and so it says that the charge density on the surface is equal to the charge density we gave it, which is exactly what we expect to find.